what this term does, see, this is the new piece. All right, so what I did is I took the old model and I modified it in some way. Now, just to kind of get an idea of how this modifies it, tell me something about, if this is a population growth problem, right? So we're looking at something growing. We know K is a growth rate that's a positive number, right? Population, that's also a positive number, right? If you look at, in fact, come back here, let me illustrate it back here. Since we know K, the growth rate, is positive and P, the population, is positive, this says dP dt is always going to be the product of two positive things. You know the product of two positive things is always what?
Positive.
Positive, good. So if you always have a derivative equal to something which is positive, tell me something about P itself. In other words, if I tell you that dP dt is always greater than 0, what do you know about P?
Greater than 0. Always increasing.
It's increasing.
Wait, what?
Always increasing.
Always what?
Increasing. Does that make sense? In fact, you can see it when we actually solve for P. Well, now you see what's going to happen is, what we want to do is have that derivative kind of taper out. Well, it was already pointed out, Christian said, shouldn't it realistically kind of do something more like this, right? So the extension in green would be the modification to the model to make it more realistic, because you know that whatever you plated has physical boundaries, and it's not going to be able to exceed whatever those physical boundaries are. So this term allows for just that, because as P approaches M, what does this term get close to? You know, let's suppose M is our maximum capacity for whatever it is we're talking about, right? In this case, Petri dish. As M gets really close to P, then M minus P gets really close to 0. What does something with a 0 derivative look like?
A line.
A line. So if it's getting infinitely close to 0, but never reaching its maximum capacity, you see how it's going to just kind of
Asymptotic.
asymptotic, right? And you see that'll produce this kind of effect. So, you know, from the mathematician standpoint, you can kind of see this as you build it in. But what you can do is just take this model now and actually solve it, and then see what the resulting function is and graph that resulting function. So let's go ahead and try it. Again, what I'm going to use is this technique we call separation of variables.
Do you multiply everything out? Or
No, I'm not going to. In fact, what I'm going to do is just pull this to one side. The reason I'm not going to multiply it all out, Christian, is because of the integration technique that I like to employ. So here we get a little more math. You know, I'm trying to make this very physical in a sense to show you guys the relevance. But at some point, all of a sudden, this becomes a math problem, right? Regardless of what physical setting it's in, all of a sudden we have to integrate this left-hand side. So just looking at the structure of the integrand is probably one of the more complicated integrands that I've had tonight so far. What kind of technique would you employ on that?
partial fractions?
Partial fractions, you got it, that's exactly right. And that's why I didn't multiply it out, Christian, because you would have had a factor in anyway to do a partial fraction on it. So I'm going to go ahead and just do a partial fraction decomposition on the 1 over P times M minus P. I guess I can multiply it out first.
Yep. Sure. I don't know what it came in which works through.
Yeah, I really don't want to write my life anymore. I want to be faithful. Send me a couple of cards.
Are you guys okay with that?
Thus far.
Thus far, good. All right, so what we then get from this
That's, you have a times n at the bottom, 1 equals a times n.
And then what we're doing is we're solving for the a.
Right.
Yeah, that a looks different than the other a's, I'm sorry, I don't know why. And now, okay, so at this stage, what do we do?
Break it up into two different integrals.
Yeah, just integrate. We integrate all the way through.
So we can pull the 1 out of 1 over
Yeah,
m
remember
out.
1 over m's a constant,
Okay.
yeah. So I did, yeah, I should have specified that, right? This is a constant going back to, because I'm assuming that whatever plate we put it in doesn't change in time. Yeah, so that's, if you wanted to have something like that, then you could build it in, right? If you had a way to represent then how it changes with time. All right, so this gives us 1 over n times ln of p. Actually, this is going to be a minus. And I think I may have just taken one too many steps. Let me back off a little bit.
Yes, please.
So, over there, what does that say? It's equal to the integral of k?
Yeah, that's a k.
And where's that k coming from? Up here, okay.
The growth rate.
Because you have a negative p.
So why?
Because you have a negative p in the ln on the bottom.
Here. That's intentional.
Yeah, why?
Good question. So when you integrate, how do you actually do that integral?
Negative p plus m.
Howard, wouldn't it just be 1 over what's on the bottom?
What would be the ln of?
Yes, okay, so, well, it's gonna be an ln, right?
Right.
But take it in like little baby steps. So Daniel, it is 1 over whatever's at the bottom, but, so be more specific about that. So you would do a u substitution, and you would let u equal what?
M minus P.
Good, that's right, yeah, you would let u equal m minus p. Now notice when you go to calculate du, do you see you get a negative dp?
Okay.
That's where it comes from, Jessica. So when you rewrite that, you actually get that the dp that you have in the integral is actually negative du, right? So this turns out to be,
Why is it negative?
because what's the derivative of negative p with respect? Did you see right here?
With respect to what? P?
Well, I'm calculating du dp, right? So if we have this quantity, and I ask you what is du dp, what's the answer?
1?
No.
Minus 1?
Yes, that's where the minus comes from. Yeah, that's where it's minus 1. So we're getting there, right? We kind of have a solution for it. We're still going to have to do some modifications to solve explicitly for the population. So one of the things I'm going to do here is actually rewrite this as a log of a quotient. You guys okay with that?
Hmm.
Funny business right there. It should be MC, but again, m times an arbitrary constant. So I think that's what irritates people the most with differential equations until you get used to it, because that arbitrary constant becomes such a trash compactor for constants.
So when in the last problem when we're doing Newton's problem, we figured out what c was going to equal. So how do we know that it's not m times something that c equals?
It could be. But now you see, again, we're going to be able to determine when we plug t in what that physically represents.
Oh, okay.
And then based upon that, we can even figure out what the units are and things like that.
So you wait till the very end.
Yeah, you do wait till the very end.
Okay.
And that's so there are really two kinds. There are what we call initial conditions and there are what we call boundary conditions. Because, for example, all these problems depend on time.
Okay.
But you can imagine problems that depend on not time, but an x value or a space
Right.
value. And you don't have to make it at x equals 0. You can, for example, I don't want to get ahead of myself, but let's say you've got a vibrating string, kind of like a guitar string, right?
Yeah.
And the guitar string is fixed at these 2 points. Then you can specify at those 2 points that the position is 0 and the velocity is 0, and you see that you'd have one at x equals 2 and one at x equals 10, right? So really, they come in 2 varieties. Either